Yes. Very well. So this is the last lecture, and I'm going to pick up where we left last time with the iteration which is supposed to, and it can be proved, to actually produce a dissipative solution for the Euler equations. We left a couple of things open, but rather than actually going through those couple of things that we left open, I will discuss directly the Hölder convergence, because to deal with the Hölder convergence, we will have to cover some of the things that I left open anyway. So it would sort of be some kind of repetition. So now that we have some idea of what is the scheme that I want to run, or that we want to run, which, by the way, if you look at it, there's not that many things that do really depend on having the Euler equations. I mean, there are some structural things that you need to be able to kind of conceive a scheme of that type. And of course, there's many structural things that you need to actually finally prove that it does work or it does converge. In a lot of situations, it wouldn't work. But it's sort of general. And if you think about it, what you actually needed, you needed some nonlinearity somewhere, because you needed that sort of resonance between Fourier modes, which actually helped you to cancel the error, okay? And then you needed some structure that makes you invert some differential operators to actually account for the error, so that you can gain from the oscillation of the perturbation that you're putting. And then, of course, you can try to carry that analysis for some other equations, and you can try to derive what we call the cell problem. That is, La'szlo likes to call it that way. I call it the master function, which is this big W, okay? And to get some idea whether you can run the scheme. And in reality, as we have just seen, even just the master function itself doesn't work for Euler if we do it brutally that way. It still needs some massaging, but it's a good starting point, I would say, in general. Okay, so now we're trying to produce a sequence VQ, PQ, and R circle Q. So this is the goal for today. Okay, solving this Euler-Reynolds system, which I'm going to rewrite. Okay, in an inductive fashion. And the goal for today is to, in fact, construct so that you're converging in C0 alpha for some alpha. And we want to see that we actually can get to the Onsager conjecture. I'm not going to discuss the dissipation part. I mean, why the energy can dissipate. We discussed it last time, and there's not really any difference between the Hölder case or the continuous case. It starts being more complicated when you actually get to the proof of the Onsager conjecture, because of something which is called gluing technique that we will have to use. I will have to explain. Probably I will get actually to this gluing technique only at the very end of the lecture. I hope to get there, okay? But I'm not going to discuss it. It's not too different from what we actually described last time. Okay, so I'm going to call the difference between two consecutive iterates VQ minus 1. I'm going to call it WQ, okay? And like it happened with Nash, right? R circle, so R circle Q in C0, I'm just going to, so here I put this little twiddle, meaning that maybe there's a constant in the inequality. So I declare this to be less or equal than some, or essentially comparable to some sequence delta Q plus 1, okay? And because the upshot of all of the system is that when I add actually the perturbation, VQ, I'm trying, so when I add the perturbation VQ, WQ, I'm trying to destroy the error that I had at Q minus 1 step, okay? And there is this geometric lemma. The geometric lemma is really structurally exactly similar to the one of the Nash scheme that I described in the third lecture. And so you expect that the size of what you actually add is going to be the square root of what you have to destroy. And when you're adding the perturbation, maybe let us put it in this way so that it's sort of more clear, right? When you are adding this perturbation, you are trying to destroy this error, okay? So, and that's why you lose a 1 in the accounting for this size, okay? So this is what I'm going to assume as well. Okay, I'm putting this twiddle over here, but really it is going to be exactly of this size, essentially, if this guy is going to be exactly of that size. We will only prove inequalities, but so maybe let me put an inequality over here too. We only prove inequality, but this is really what is actually happening during the scheme. It's roughly of that size. Okay, and then I will have to kind of oscillate, and so I'm going to assume that the size of the oscillation is going to be roughly delta q to the 1/2 lambda q. Okay, so this is kind of the parameter that we call lemma is how much I oscillate actually at the step q. And it stands to reason that this guy is not going to converge, because if this guy converges, you would converge to a C1 solution. Certainly it's not going to converge. It's going to explode. It's going to explode in a fashion which is exponential, if not even faster, like double exponential. So because of that, all of the things that you're adding before in your estimate is essentially even milder than this guy. So it's really like this guy which is leading the overall size, and so this will actually imply that this one is of the same size as well. Okay. Of course, you expect a very similar estimate on the C1 norm of this guy, right? I mean, this one also kind of, when you produced it by adding VQ, which was oscillating at a certain scale, okay? So you're expecting, therefore, even this estimate. Okay. Roughly, I'm expecting that each time that I'm going to compute the derivative, I actually increase like my estimate by a power of lambda q, by adding 1 lambda q factor. So second derivatives will scale in a similar way and so on. Okay, so I should discuss also the perturbation for the pressure. And it actually, I'm not going really to discuss it that much, but you can imagine that the pressure actually behaves sort of quadratically compared to compared to the velocity. I don't, just trust me on this. It comes out of the computation. One could guess that this is true because the pressure depends actually quadratically on the velocity, but of course you are adding all the things, right? And so you would have actually to sort of make an expansion and argue why somewhat the cross products between VQ and VQ minus 1, the cross products that you would have actually when you make the expansion are not too bad. So, but just trust me on this. So much more interesting is what you can expect on the advective derivatives. This guy. This is really like this part of the equation, right? I mean, this I've written this way because I want to pass it into the limit, but it's really this term, which along the iterate, I can actually really write in this term in this way because I'm smooth, right? So I can carry on all the computations I want. So this is the advective derivative. So it is derivative along the flow. And of course, because it is if you put the gradient of PQ on this side, it is of the size of the gradient of the pressure, which is going to be of the size of delta Q lambda Q, because the pressure will also not converge in C1. See, if the pressure were converging in the scaling of our kind of exponents, you would get actually to C1/2 solutions, right? I mean, because this would mean that right, so this would mean that delta Q to the 1/2 times lambda Q to the 1/2 is actually converging, okay? And that is exactly the C1/2 scaling. And we know by Onsager that I cannot actually converge even better than C1/3 because I have energy conservation after 1/3. By the way, I didn't give you that computation, but Hyunju told me that she actually covered it. So I'm not going to do it. So it's interesting, therefore, to kind of guess that it improves compared to the kind of silly estimate. Because you see, I could make the estimate separate. I could estimate the time derivative by using the equation and putting all of the things on the other side. And of course, this guy is going to be as big as the derivative of VQ. So I would get actually delta Q to 1/2 lambda. So it improves by a delta Q to the 1/2. Now here, there's a very important observation, which was done by Izet for the first time in the work leading to his PhD thesis. Actually, even the advective derivative of the Reynolds stress improves by this factor delta Q to the 1/2. Okay, it's far from obvious, but you can imagine that because, I mean, you can imagine because of the following. The way we are actually going to construct, the way we hinted we are going to construct, is to actually make our WQ like something which is fast oscillating in space, and then it's advected along the flow. So approximately this guy, which is actually reconstructed by, you know, inverting the divergence operator on those terms, has the hope of being partially advected along the flow. And so to actually behave better than just being, you know, what happens if I take the time derivative and the space derivative of this guy. Okay, so these are the inductive, yes? No, it's delta Q to the 1/2. Because it's not like, sorry? This one here, yes. Oh, yeah, no, it's power 1. Sorry. It has to improve compared to this guy. Yes. No, it's power 1, sorry. Thank you very much for pointing that out. I mean, it should get better than the estimate that we have for the spatial derivative, not worse. Okay, so at this point in my discussion last year's, on Tuesday, so we wanted to kind of, so we wanted to run WQ to be a function big W, or WQ plus 1, to be a function big W. Let me put accent. Right, to be a function big W, what we call the master function of VQ of xt, R circle Q of xt, and then we have lambda Q plus 1x, lambda Q plus 1t. Okay, and then we said this is not going to be divergence free, but we add a correction by inverting the divergence operator and we make it divergence free. And I'm just going to forget about this correction because we already argued it's going to be much smaller. Okay? So then we derived conditions for big W. By the way, I declared it at the beginning of every lecture. I declare it even now. Now I'm following really the survey that I mentioned for the last lecture, just a survey. And then at a certain point when I am towards the end, I will follow some other references and I will tell you where things appeared that I'm going to say, okay? So what were the conditions for W? So, so this is a function w of x and t, psi and tau. Okay? So we want w let me call it hypothesis 1. We want w to be 2 pi periodic in psi. And remember that when we were expanding in Fourier series in psi, we wanted the zero mode of the Fourier series to disappear, to be 0. And of course, that means that the average of w in psi is equal to 0. Okay, so what do I mean by this? Of course, by this I mean just the average over the periodic torus of w of x, t, psi, and tau d psi. Okay, so that's what I'm always going to mean by putting this thing over there. Okay. Oh boy. Here I wanted to, so I don't want to do this. Remember that I want to do this for some function fq of t of the identity plus, right? So that, right, so this is not a function, sorry, this is not a function xt, sorry, it's a function of v and r. It becomes a function of x and t when I substitute for v and r the values. Right, I mean, I wanted to add, remember we discussed this function of time times the identity. This is what actually, the degree of freedom that we add to adjust the energy. And the reason why we want to add this is because this guy is trace free. We will not be able to actually solve the next equation I'm going to write because of some convexity. Okay. So this is the next that I want. So the average of w tensor w in psi should be equal to r. Then I want the PDE that we derived to be satisfied. So this is d tau w plus v dot grad psi w plus divergence psi of w tensor w equals 0. Then I have divergence psi of w equals 0. Now, oh, gradient psi p. Okay, and p is a suitable pressure. So this is again a suitable function which is going to depend on v, r, psi, and tau. Okay, and then I want estimates on this guy, right? So what estimates do I want? Okay, of course I want w to be smooth. Now, the size of w at a point v, r, psi, and tau, because of this, I'm expecting it's going to be roughly the square root of r, of the size of r. This is the only thing which is going to be compatible with the estimates that I have. Okay, but I also want the v derivative of this to have the same estimate, okay? Because I want smoothness which is independent of kind of the other variables, which are psi and tau. It shouldn't get worse, even for very large time. It cannot get worse for psi because psi is periodic, but tau is not periodic at this point, so. Now, the r derivative, though, of w can't be bounded. Of course, it's like when you're taking a derivative of the square root, so am I expecting this guy. Okay. And So what we remarked last time is that, unfortunately, there is not a master function which is satisfying H1, H2, H3, and H4. If you remember, we actually had a master function which is satisfying this guy, a stationary one without depending on V. But when we were trying to actually transport the guy, what happened is that we were violating this basic estimate over here. So the derivative in V wasn't bounded anymore, okay? Because it appeared in front, it appeared on a face in front of the time. And so the estimate that we would have gotten was like an estimate like this times the time. But because in the time I'm actually going to put a lambda, that it was going to destroy my estimate. Okay, so the upshot was it does not exist. So this was the remark. W does not exist. Now, but it will not serve my purposes anyway. Somewhat. This is going, not exactly, but somewhat, this is what we are trying to actually going to use in a second. Not to make the time too large and try to solve it somehow for short times. Of course, this doesn't still serve our purposes because it means we would have to use different W's for different kind of time intervals, which means that we will have to patch these W's together somewhat, which is still introducing some other errors because as usual actually observed, if I'm trying to patch two functions, like saying using a partition of unity, for instance, which are defined on somehow very small domains, I will need to pay an error for the cutoff, for the derivative of the cutoff. And it will be a worse and worse error as I make actually my interval narrower and narrower. Yeah, we will try to do something like that because the estimate is violating for large time. And that's what I hinted somehow towards the end in the first C0 paper. Like, rather than sort of making the time small, we discretized the set of possible velocities V, so that it's not varying with V anymore. So then the derivative in V would be equal to 0. But then, of course, I can't solve it for every V. I can only approximately solve it for every V, and I would get an extra error. And then my iteration would get that error. Anyway, the upshot, for which I'm not going to show you the computation, is that given those estimates that I've written over there, and given the master function, you would actually get a C0 1/3 convergent scheme. Just barely. So this means that I really have to be, so I can solve this by putting an error, say. But if I'm solving this by putting an error which is a power of lambda, I will never be able to actually converge in C alpha. In some sense, I need actually a mechanism which introduces an extra error in this equation. And this extra error is going to be as small a power of lambda as you wish. Like, or, in the ideal world, something like a log of lambda. And then my estimates will not be perturbed and I will be able to converge. Anyway, I'm not going to show you this particular estimate, which actually makes you converge to C 1/3, because we will see it, we will see somehow along the way that at a certain point, I will get actually partial results, and then I will see that in the end, I'm going to get the C 1/3, and you will recognize what I mean by that. Okay, so W does not exist. So, and because W does not exist, we are going to modify our ansatz. So there are plenty of stationary guys that do actually the job. And I will give you an example. Sorry? Sorry. Maybe I call it WC. The correction, yes, and actually in the survey we call this WO because for oscillation. So this is the We call it, this is the oscillatory ansatz, and this is, sorry, the correction, yes. And together they give you WQ plus 1. Okay. Whereas if you remember, I'm not covering this again, RQ plus 1 was actually solved, was actually found by solving for the divergence inverse operator. Okay, so I was just plugging into that. Okay, so there's actually plenty that do the job with the WS. So for these, we get plenty. Okay, for this, we get plenty. And so because I'm somehow now needing, I'm going to need these assumptions along my rest, the rest of my fast expiring time. Let me compress that request over here as assumption 1. And let me compress the assumption 4 over here. Of course, I also need kind of similar estimates for the pressure, because then I need to run also the arguments on the pressure. So I will mostly actually not care about it. You will need to actually go there and see the computations for the pressure too. It's annoying. I can't completely ignore the pressure because it will enter into the estimates for my V as well. So I will need to do something. But it's mostly harmless. Okay, so let me put now here the hypothesis that I have. Okay, and these guys I don't want to cancel. I will always hopefully have them in here with me. Okay, and at the same time, I don't want to cancel the inductive estimates. And so let me copy the inductive estimates over there, and then I will just need somehow this side of the board. Okay, so so what are the inductive estimates that I want? Okay, so they are those guys over there. So let me these are one guys. And then I have the pressures. Okay, so and now let me cancel everything else. Okay, so now let me let me ignore that there is a correction term. And let me just plug in for the definition of R circle Q plus 1. This is a computation that we did last time. But so when I look at R circle Q plus 1, I will have minus, and then I have this operator which I call R. This is what actually inverts the divergence, right? Okay. Let me give up to what we actually do in the survey, in which we actually call it divergence to the -1. But it's the matrix operator. Okay? So you will get a guy like this. Let me also call this thing over here RQ, so that I don't have to care about what it is. This one is really armless, and I'm going to assume FQ in C0 is less or equal than delta Q plus 1. And even from this side. So, okay, let me maybe do it this way. This is really what is going to happen. And I will have similar estimate on time derivatives. Okay, so there's this guy, and then there is gradient of PQ plus 1 minus PQ. Okay, and then there is this guy. Okay, so this is what we call the Nash error. Okay, this is what we called the oscillation error, although I challenge my old self that we call it that way. And now you see what is this transport error which is appearing all the times in the other talks, right? So where does it come from? From the fact that I cannot exactly solve the transport part of the equation, okay? So that is the transport error. Okay, so here, remember that we had a way of actually doing this by making this this partition of unity on the velocities v and making stuff and so on, which it's kind of funny because it got surpassed by the idea that I'm going to tell you by EZ. But actually, when you go back and see what is our current world record on the local energy inequality, we are actually resuscitating that idea. I think it's still a cool idea. And so now, I'm going to be very ambitious. So I would know what to do. I would know what to stick over there if the velocity were equal to 0. I would just stick the stationary flow computed on R circle Q and then fast oscillation. Okay. Now I want to solve that transport equation. So what I could do is okay, VQ is a smooth function. It has a flow. I just transport it along that flow, okay? And this is Phil Isett idea implemented in his PhD thesis. Okay. Eventually, because by combining our ideas with Ristambach master and his idea, we would get actually much, much shorter proof, and there were things were appearing at the same time. We actually have a paper all together, the 4 of us. And so that actually gets this exponent 1/5, which I'm describing right now, how to get there. So now I'm going to assume that WQ plus 1 is then of the following type. So it's going to be a W, okay? So there's going to be over here R circle, so the stationary guy, so there's going to be here RQ of XT. And then because I'm actually transporting, instead of having X, I mean, how do you transport, how do you find the solution of a transport equation? You compose your initial data with the flow, right? And so here I have lambda Q plus 1, but instead of putting instead of putting X, I will put actually the flow, right? And I have no time. I have no time, so this stationary function now does not need time because the equation does not, I mean, the equation does not have any time derivative, right? Any fast time derivative, right? There is no d tau. Okay, this is what I want to do, but it's obvious that this idea will certainly suck at a certain point because, you know, VQ is getting worse and worse in the C1 category. And so phi Q is actually getting worse and worse. So what do you have at disposal actually to estimate what is the derivative of phi q, right? You essentially have Gronwall. So if you try to estimate what is kind of d phi q, so phi q starts being the identity. If you kind of try to see how it deviates from the identity, you have an estimate of the following type, something like, you know, exponential of the dvq times t. And now here you would have to say immediately, oh my God, I actually want to, you know, in our scheme, I want to, you know, get an error which is like, I don't know, a small power of lambda q, and there I have an exponential. So this is going to be very bad. -1, actually. You have to put a -1 over here, right? Because this phi q at the beginning of the time is the identity, okay, when you're solving for it. So that's a -1 over there. Now, because there is a -1 over there, then you know that this is going to be less or equal than dvq times t for short times. For short times. And it is wonderful at that point, at least maybe not so wonderful, but, you know, sufficiently wonderful. So for time t's, which are kind of the reciprocal of delta q to the 1/2 times lambda q, I can actually hope of treating this object as a perturbation of the identity, okay? So on this range of time, I'm fine, but this is a particularly small range of time. So what I can try to do, I can try to construct my perturbation WQ plus 1 as a sum. And now here I'm going to have kind of cutoff functions. So on a partition of, so there's again a partition of unity, but this time it's only, this time it's only in time. So a partition of unity in time. And then I'm going to have WS RQ of XT. Okay, it's time to cancel also this part. And then I'm going to put here lambda q plus 1 phi q of xt. Okay. And what this phi q of xt does, so it's, so phi k q of xt solves the transport, but not by being the identity at time 0, but by being the identity at some time phi q, so which depends on k. So, and the time is going to be what? So let me call it k over mu. Okay, and this is going to be equal to x. So I have my time. I chopped it into pieces, which overlap a little bit. And these are the times, for instance, this one is like 1 over mu. This one is the time 2 over mu. And these intervals, they are of size something like, I don't know. When you think about it, it would be like 2 mu going from here to there. And so let me just say it's, I don't know, 7 over 8 mu. So there's like, you know, they overlap with each other. Okay, these cutoff functions depend on mu too, right? So, and they are cutoff functions of the following type. Okay, so can I do this? Because I'm taking linear combinations of, you know, my perturbations. Well, I could do this if, for instance, I find a space of solutions over here, which is solving that problem, which at the same time is actually a linear space, so that I can take, like, you know, combinations of them. And this was possible because already in our C0 paper, we wanted to do, you know, partition of unity. And so already there, we discover actually not only a manifold of solutions which satisfy this property, but really a linear space of solutions, okay? So they are called Beltrami flow. So this can be implemented because there are Beltrami flows, which I'm not going to describe though, okay? Now let us see what is going to happen over here, right? So now here I need a little bit of help, okay? So what is the error that I'm doing in the transport? So let me call it, this guy, the transport error. Okay. In the transport error, when I have to take that guy, right? I mean, the dt wq plus vq dot grad wq plus 1. When I'm differentiating this guy, I actually get 0, right? But unfortunately, there's a time derivative of this guy over here. I'm trying to make a function which is equal to 1 and compactly supported on an interval which has size 1 over mu. What is the size of the time derivative? It is actually equal to mu, okay? So the transport error will have a C0 estimate, which is less or equal than mu delta q plus 1 to the 1/2, right? I mean, because this guy is of the size delta q plus 1 to the 1/2, okay, by my idea over here, by my estimates over here. Okay, what is about the oscillation error? Okay, so the oscillation error, so remember there was a part which was supposed to completely cancel, right? And that part was kind of the, you know, WS, tensor WS. So to understand the oscillation error, recall that in our ansatz, the WS was what? So the WS of R and Xi was something like the sum over K of AK of R, and then it was e to the I k dot psi, okay? This was perfect, right? So now, if I didn't have to actually compose with the flow, right? I had exactly this shape, and I had, like, you know, lambda q plus 1 x. So when when I sort of like, do this, I really have what I want, which is this guy. This is what we really run the, argument that it was going to cancel the R circle Q or the RQ, okay? But now you see it's not true anymore that it takes this shape. If I put a phi Q, my actual thing is a little bit different. It's going to be, so my WO, or my W really, well, it's really my WO now, I mean the one which is oscillating. I'm completely neglecting the corrector that I have to put for divergence-free condition. So the WO of xt now is actually quite somewhat different, right? What is the somewhat difference? So the somewhat difference is that it's going to look like something like this. AK of RQ of xt, okay, times e to the I lambda q plus 1 phi q of xt. And remember the reason why I was being killed in the first attempt when I was solving the full master equation is that the bloody V was appearing over here, right? And so again, it appears over here. So, the first reaction is like, well, fuck, I didn't solve anything actually. But if I really want to apply the ansatz of before, I really have something like this. So now if I think about it in this way, right? If I think about it in this way, look, this one is correct. Sorry? Oh, because I need to take a Spada product here with this guy, right? Is the Fourier wave number, which I forgot along the computations. Thank you. Right. Otherwise, I'm taking an exponential of a vector, which is not a safe thing to do. Right? So now, see, because I have this estimate for small times, so for times which are much, much smaller than this guy, okay? This one looks almost like 1. Okay? So, how is this going really to work? Well, this is going to work in the following way. So let me call this one. Okay, now I have too many k's, right? I mean, because actually there's the k of the because there is the k of the frequency and there's the k of the cutoff function. Now, here I should have used a different k, so I should have used j. Okay. Okay. In the survey, in fact, it's a j. I mean, I tend to underestimate my younger self, but sometimes I was less dumb than I think. Okay. and so here there's a j. Okay, and here there is the, you know, phi k j. Okay, and when you actually insert the when you insert this into the divergence operator, so the error that you actually do, if you remember our ansatz, the error that you do when you're actually trying to understand this, I mean, if there were no coefficients, that would be a perfect cancellation. So now there are coefficients, and if you remember the error that we got from our stationary phase analysis, essentially, is that it depends on the derivative of the coefficient divided by lambda q plus 1, okay? So if I call all of this kind of, okay, so actually maybe phi chi j is going to be this guy. So the oscillation error is supposed to get something like this. It's going to be less or equal. And then I'm going to have kind of, you know, the derivative of this quantity divided by lambda q plus 1. Now remember, the derivative of ak is what we already have in the Nash error. And in the Nash error, we already know I have delta q plus 1 to the 1/2, delta q to the 1/2, lambda q. That is so good that it would actually get me to a C1/3. So, sorry? Derivative of square. This amplitude. Yeah, it's this amplitude. No, it's more like this. Yes, yeah, this amplitude squared. Yes, 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 thank you. Yes, exactly, it's this amplitude squared. And now what I'm just going to, okay, so which is going to be this guy, right? And now what I'm going to argue is that when the derivative actually falls on this, I'm pretty good. This is even better than the Nash error, right? I mean, because it has something like delta q plus 1 times lambda q. Okay? So it really hurts me when I actually differentiate over here. And so if I differentiate over here, I get delta q plus 1 from this guy. Okay? I have the over lambda q plus 1 in here. And then I have the derivative of phi kj. Now, phi kj, the fact that it's squared, it doesn't matter to me, right? Because it's a complex number with modulus 1. So the square is not actually doing anything. What it's doing is like, you know, the lambda q plus 1. Okay? And, okay, I get lambda q plus 1. Oh God, so this actually eliminates the thing with which I wanted to gain. But then I have the derivative of phi q minus the identity. And so this is going to be what? Or something very ugly, right? This is the estimate. Something very ugly because this one is delta q to the 1/2 times lambda q. Okay? But for a short time, t, because I'm restarting my flow every time with the identity being here, and I'm only considering a short interval of size 1/mu in there. Okay? And so here you actually gain the mu. Okay? So this is what is going to be the oscillation error. No, so mu is large, 1/mu has to be small, 1/mu has to be less or equal than this guy, because after, and this is what we called CFL condition, Courant Friedrich-Lars condition. That's because when you're writing a fancy survey, it's always good to actually, like, you know, call big names like, I don't know, Gromov and so on. But actually it has a, you know, it has a serious reason. So this is a condition which is very well known in numerical schemes when you're discretizing, and which is coming from a similar issue, right? There's a certain time after which a certain type of discretizations are not going to be good anymore. And the reason why is very similar to the reason I'm giving you here. If you're transporting along a vector field which has a certain C1 norm, it is a flow of diffeomorphisms. This is like what, calculus 2 tells you, like, back in the day when you were, well, for you, it's not that long ago. For me, it's very long ago. But then past that time, the derivatives are actually degenerating with an exponential growth. And that is terrible, like literally terrible. So I definitely don't want to go past that time. So the inequality that you want on mu is that 1 over mu is less or equal than, or is approximately less or equal than 1 over delta q to the 1/2 times lambda q. Mu is actually a large parameter. 1 over mu is small. The reason is just psychological. We could have used, some people ask me, why didn't you use tau for 1 over mu? Because it's a time. I don't know. Tau was already taken actually over there. But so we want this one less or equal than that guy, okay? Sorry, bigger or equal than that guy. And you see that it stands to reason, right? Because it's in this denominator. So mu not only has to be bigger or equal than this guy, but it has to be sufficiently big so that it's kind of eating up your delta q plus 1 over here, okay? So the Nash error has the same estimate as it had for the Nash iteration. So I'm not going to write it down. Okay, so now you've got your parameter mu to choose, and let us write down what are the conditions that I need to satisfy to be able to close the iteration, okay? So that is the transport error, and that is mu times delta q plus 1 to the 1/2. Okay, that is the oscillation error, and that is this delta q plus 1, delta q to the 1/2 lambda q divided by mu. Okay, and there is the Nash error, which is this guy. And what is the condition to be able to iterate this ugly scheme? I need to be less or equal than delta q plus 2, because that is what is going to be my next target for the Reynolds stress. Okay? Well, now this parameter, I've never chosen it. You see, you want to choose it in such a way that this quantity over here is minimal, right? It's a very simple optimization problem, right? So the sum of this guy is going to be minimal when you actually choose mu so that they balance each other, okay? So you know what you have to choose. So mu has to be chosen to be mu squared, then I divide it over here, so this has to be chosen in this fashion. Okay, so now, exercise. So choose it, put the usual ansatz, so lambda q equal lambda to the minus q, and delta q equal to lambda q to the, lambda to the q, and this one is lambda to the minus 2 alpha. See which alpha actually allow to close this inductive assumption, and you will find that alpha has to be less than 1 over 5. Okay, and that is kind of the iteration at which we get. I mean, the Hilder exponent at which we get. No, mu has to be much larger than delta q to the 1/2 times lambda q. It's a very, very valid point. I did get something smaller. It seems so. So what did I do wrong? Okay, the oscillation error there is correct. The other one is correct too. I actually got something that you're saying it's smaller. It's a very valid point. What mistake did I do? Possibly a computational mistake. What was the transport error? Wait a second. Where is the first error?
This is mu squared equals.
Oh, wait. So in my, okay. I actually have this in my computations. But I'm failing to understand why. Sorry? Yeah, the inverse divergence, but when I'm differentiating this, I get a lambda q plus 1 in front, and then it's divided by that.
That's the transport error.
Sorry?
Yes, the transport error.
Oh, right. In the transport error, I'm getting the 1 over lambda q plus 1. Sorry. Yes, of course. Yes. Because I'm inverting the divergence, right? I mean, otherwise it gets worse than before. So there's no way I can close that. Yes. Thank you very much. No, this one here is correct. So it's in the transport error, I'm getting the 1 over lambda q plus 1. Yes. Thank you very much. Okay, so now it stands to reason that this one is better, right? Otherwise, it's not a time scale. Yes. Otherwise, it's not a time scale because it would be like 1 over delta q to the plus 1 to the 1/2, right? Which is very large. Yes. Okay. Thank you. Let me see that it corresponds actually to what we really write down, but I think so now. Yeah, I think so. So this guy is becoming this. Right, which for instance means that when I plug it inside here, I get this, that, this, and that. And you should sort of see somewhat, okay, it's not completely clear, right? I mean, because this one gets a little bit better than that guy, but this one got much worse, right? Because lambda q divided by lambda q plus 1 is supposed to be kind of very large. So you should see by our kind of considerations that this guy is actually larger than this guy. So really, this one doesn't matter, and what you actually have to ensure is that this guy is less or equal than delta q plus 2, and if you do the exercise, you get to alpha equal 1 over 5, which I'm not going to do. Okay, thank you very much. So now you see that there are two issues that at first kind of make you wonder whether you can close this estimate at all, right? So first of all, I need to try a way not to cut off, or to cut off as little as possible, okay? But the other issue that I have is that I need to try to diffuse the fact that over here I have, this guy, okay, which is spitting me out when I differentiate the derivative of phi q, okay, which is sort of bad. So here is an interesting first input. By the way, another remark. Assume you could actually run your, assume you could run your kind of transport until the maximum which is allowed to me by the CFL condition, okay? And then I will need to cut off. Then I need to put here delta Q to the 1/2 times lambda Q. Okay? It would be perfect, right? I mean, because it's exactly the size of this. So the upshot should be that if I were able to pay no costs over here, literally no costs, and if I could run my transport up until kind of what is allowed to me by the CFL condition, then actually I would have exactly what I need to close a scheme which gets me to C1/3. Okay? So here comes the first interesting or breakthrough. So there is a paper by Sara Daneri and La'szlo, in which they devise a very, very simple solution of this stationary guy. Okay, so they're the so-called Mikado flows. Okay, what are Mikado flows? So remember that you want a stationary flow in 3 dimensions. So take a pipe flow, which is going into a certain preferred direction, which gets periodic, right? I mean, which gets periodized after some time. So how do they look like? So they look like this. So there's a certain, okay, so V of, V of X. So this is going to be a cutoff function, say phi, which is going to make somehow my flow compactly supported over here. And it's a cutoff function which depends on the kind of cross section of this cylinder. So here there's a cutoff function phi, which depends on the projection of X, say, let me call it this way. So projection of X on the plane pi. Okay, and then it's going to be otherwise a fixed velocity, say V0. Okay, and pi is orthogonal to V0. Okay, you see right away that the divergence-free condition is okay. The other thing that you see right away is that that you will see right away if you make the computations is that it doesn't solve divergence of WS tensor WS exactly, but it actually solved, this one, but it actually solved the stationary transport equation, okay? So WS is really transporting itself. You kind of see it, right? I mean, because it's going, right? I mean, it's going kind of in this direction. So everything sort of gets kind of flown into this pipe. Okay? So why is that a great thing? That is a great thing because instead of using this ansatz here, I mean, of course, now what you're going to do, okay, so first of all, you have to actually imagine that when you're going to take now the average of this, right, the average of this is going to be something like V0 times tensor V0, okay? But you can put a lot of pipe flows over here which don't intersect, and you still have a stationary solution. So you arrange many of them without self-intersecting. You just need to be somehow small with a cylinder. And then you can run this geometric lemma. I mean, you just need finitely many of them. And then you can generate any Reynolds stress. And you have your master function Ws. Now, what you're going to do is you're going to kind of expand the master function in Fourier series of Xi so that you get a writing of the following type. But instead of making that ansatz, you make a different ansatz. And the reason why you're able actually to make this different ansatz is because the pressure disappeared from the equation. So the ansatz that you now make is modified to the following. What is it? Okay. I need to change paper. And now, this is, of course, the ansatz that they have in the paper by Daneri and Sze'kelyhidi, but, you know, if you want a kind of quickest proof using La'szlo and Sarah, and then we will see IZ ideas. So what I will be following is a paper by Buckmaster, myself, La'szlo, and Vicol, which is called Onsager's conjecture for admissible weak solutions. Okay, so the ansatz you actually do is slightly different, but not much. And it is the following. Okay, where is the guy? Okay, here it is. Okay, so you're actually putting your perturbation which abide to the following formula. So it's going to be the sum. Okay, then you have the AK that you have over there of RQ of XT. Okay. And then you have d phi I to the -1 Okay, so these AKs are actually vectorial. So maybe what I should say is that, okay, so these AKs are vectorial. Just for the moment, let me think they are some fixed vectors times an amplitude, okay? So that I can feed to this guy a vector and keep it outside. Okay, and then I have e to the I lambda q running out of space. But maybe since this is actually so important, let me rewrite the whole equation over here. So WO is going to be the sum over K. And then I have the AK of RQ of XT. And then I have d phi JQ to the minus 1 BK. And then I have e to the I lambda q plus 1 phi q plus 1 phi qj of xt. Okay. And somehow the reason why you're doing this, it's because before because now when you're actually going to make the computation, there's going essentially to be a sort of cancellation when you're taking this inverse derivative with the derivative of that guy, when you're computing derivatives. So this actually cancels completely kind of the error, but the reason why you can do this ansatz in this way is because the pressure disappeared from the equation, and so rather than solving stationary, it solves stationary Euler, but it kind of also solves transport with itself, which is a much stronger property. Okay, so I'm getting towards actually the end of my talk. So in essence, this would completely remove this error. Actually, not completely, because there are some other error terms that you have to differentiate. And in fact, to tell you the truth, you're not even exactly feeding RQ of XT, you're feeding some sort of slight manipulation of it. There's several things that you have to do correctly. Okay, so one of the reasons why you're not feeding RQ is because when you now are going to sort of put the balancing condition, this guy comes. And so the average of this is going to cancel d phi jq to the minus 1 bk tensor, right? So it's not canceling the correct thing. So you need to feed something over here which is adapted in such a way that it's canceling the correct thing, okay? So you need to modify this too. But, forgetting about these issues, essentially the paper by Sarah and La'szlo tells you a way of completely getting rid of this. But you are still not able to run the iteration. And the reason why you're not able to run the iteration is because for summing the Mikado flows in two solutions, when you're making this partition of unity, you need the supports of the Mikado flow disjoint. Okay? So now imagine that you're trying to apply your partition of unity strategy. Okay? So here you have your kind of box of Mikado flows, which, by the way, I think Sarah should have insisted it's going to be called spaghetti, but so here you have your spaghetti at the initial time, right? So they are all kind of nicely kind of distributed. Now you apply the flow, right? Now you apply the flow and they got all wiggly. So now if you want to restart the flow, you should actually be able to find Mikado flows which kind of stick inside of the wiggly spaghetti and then sort of, you propagate them again. If you're sufficiently close to the identity, in other words, if you take mu sufficiently large so that you're sufficiently close to the identity, then you will be able to do it. And in fact, while we were working at that, we did it, and La'szlo and I tried this computation. But it seems almost like a joke because you will need actually to choose mu so that you get again the 1/5. So there's absolutely no improvement if you do that. Okay? But so here there's a decisive idea, and this is the decisive idea of Phil, which was then able to close the proof of the Onsager conjecture. So it would be really wonderful if I had my Reynolds stress, which was distributed in kind of disjoint time stripes. So in other words, there are time stripes of the correct size in which the in which the Reynolds stress is actually appearing. And then I have next to it a region in which I'm solving Euler exactly. Because at that point, I could actually stay with these stripes precisely in a region where my CFL condition is satisfied. And I would just simply run this argument on that stripe and then simply not make any perturbation, because then I know I'm a solution of Euler, okay? And then again, cancel the error on the next stripe. So here's the key idea. If we could solve or localize the Reynolds stress error in disjoint time intervals, of size delta q to the 1/2 lambda q to the -1, then we don't need actually to kind of make this partition of unity and try to fit the uncooked spaghetti in the cooked spaghetti. Okay. And here enters what he calls what Phil calls gluing technique. So the idea is the following: rather than immediately removing the error, let us make a first step and perturb my solution of the Reynolds stress to a new solution that has that characteristic. And how am I going to do it? Well, I still kind of partition time in 1/μ time intervals. So here's the gluing. So partition time in 1/μ time intervals. So this is going to be again 1/μ. Now this is going to be 2/μ. Three over mu, and so on. And now what I'm doing is, here I have VQ, I input it inside here, and I solve the Euler equation with C infinity solution up until this interval. So solve Euler exactly with this initial data. So now I construct a new guy, which I'm going to call VQJ, and so VQJ solves the Euler equation. Let me write it in this way. With that initial time. Okay, so at J/μ, I'm exactly equal to VQ. And the same reason why you are below the CFL condition is the reason why there is actually a smooth solution of Euler up to that time. Because essentially Euler is very close to a transport. Then of course you have the pressure, but it's sort of somewhat close to a transport. If you're trying to close it, like for instance, by proving that there is a solution by using Kato's method, as long as you stay below the same time scale which allows you to get a good transport, you're actually also on a good time scale in which you get a classical solution of Euler. If you're familiar on how you prove actually the existence of Euler, you're kind of closing an iteration scheme in which you're transporting, then you transport, say, your vorticity omega, but then, of course, omega is not anymore linked to your V by being sort of the vorticity of V, but you sort of try doing this thing over and over again until by a fixed point, actually, you're converging to a solution. So now, this is a good solution up to here, but then it even ceases to exist, let alone, being good. So what are you going to do? You construct another solution over here, and now make a partition of unity to glue these solutions together. Of course, the partition of unity will destroy the Euler equation, but it will destroy the Euler equation over here. And of course, kind of the very interesting part is that you're able to do this, and by comparing to the old solution, right, which, the old solution has a divergence of our circle Q. So the old guy is already almost a solution of Euler. I mean, it's a solution of Euler with a forcing term. So by comparing your two solutions which they overlap to the old solution, you actually discover that they are sufficiently close. And so the radial stress which is produced as an error because you're not solving the Euler equation over here is actually going to have the same estimate that you had for the Reynolds stress in here. So only you will augment this by essentially a constant, if you want. Okay? So at this point, you actually are able to close the iteration, which gets you to the 1/3. Because now, when you insert this kind of intermediate step, I mean, before actually correcting the error, you introduce this intermediate step, you got actually your Reynolds stress, which is compactly supported in places in which you can remove it. So you will remove by using the Mikado flows over here and that ansatz, and now you make the cutoff in such a way that, your oscillation that you're adding disappears a little bit before you have to start the new oscillation. Okay? And these intervals are all comparable and they're all of size 1/μ. So the error that you do in the cutoff is exactly actually what we computed, is exactly this mu. So now you're left with the Nash error and with the transport error, but with the mu that you can choose like the CFL condition, and that is exactly matching the Nash error that you have. And now you've got your schema. Okay, so I don't think I can actually in 2 minutes do anything about the beyond. So the beyond, if you invite me another time. But okay, so thank you for bearing with me. I'm of course ready to take questions, but it was a pleasure. Yes. So PQJ is a solution for each of the subintervals, and the only important point is that it's the identity in the middle point of the interval. So it's like you're solving the ODE, because how do you find PQ? You invert the flow of the ODE, right? So you're solving the ODE by starting the particles at the central interval, and then you propagate it like, a little bit above, a little bit further in time and a little bit backward in time. Yes. No. We are transporting. Okay, no. So there's two different things. So that is the phi q that we use over there, and that is the phi q is the solution of the transport. It will be the solution of the transport for the new guy that you have actually produced over here. So, and you solve the transport by putting the identity, so it's the initial data, then instead of putting it at time t equals 0, you put at different times. So that somehow you have a you have a solution of the transport, but it's very close to be the identity because, you're on small times. So that is what you do on the transport once you have the VQ. Now over there is a different story. There you solve Euler and you construct your new velocity, which is close to the old velocity that you wanted to perturb. So there's like a two-step construct the new velocity, and then you remove the Reynolds stress for the new velocity. When you remove the Reynolds stress for the new velocity, you again make this transport, but you will make the transport somehow on this interval. So you will solve the transport here and maybe make, you know, your initial data equal to the identity in here. And you bundle everything together. But there are two different issues. So the transport is one thing, and the Euler equation is one thing, even though they they have a very similar idea. Yes. Yeah, FQT, like we discussed on Tuesday, it has to be bigger or equal than the modulus of this guy. And so now the way you run the iteration is again similar to what we described last time. So you have a target energy that you want to reach. You don't try to get too close to it. Somehow you kind of, you know, you adjust your FQ in such a way that you get somehow close to it, but not too much. Because then you need space for the next iteration to get again close to it, but not too much. And each time that you're getting closer, you need to make sure that you have enough space between you and the energy that you want to target so that you can move enough to be above the error that you have created. So let's say if you're targeting to create an error which is like, I don't know, 2 to the minus k, or let's say you're targeting to create an error which is 4 to the minus k. Now, with your energy, I mean, you want to be able to add something like 10 times 4 to the minus k. So you always want to be further away from the final energy, which allows you to add this 10 times 4 to the minus k, or something of that size. So you will want to get close to the energy, but not too fast.
Same as the previous one, so the white part.
Yes, okay, so the white part, so so you have VQ, okay? Now you produce V tilde Q, let's say, and V tilde Q you produce this by making a partition of unity of the VQJ. And now this partition of unity is going to look like this. It's going to be exactly equal to 1 over here, and then it goes down this way. And this other partition of unity is going up, and then it's exactly equal to 1. Okay, now you compute the Reynolds stress for this guy. So you feed it into the Euler equation, and now you compute R tilde Q. Okay, so R tilde Q now is going to be divergence to the minus 1 of dt V tilde Q plus V tilde Q dot grad V tilde Q plus gradient P tilde Q. Okay. And now, because you were exactly solving the Euler equation in here, your R tilde Q is in here. Now you go back to this, and you're putting the tilde in here. You're putting the phi tilde in here so that you're solving the iteration that I described to you for the new velocity. But now you want to solve it only on these stripes. So you introduce another cutoff. So now there is another cutoff, let me call it chi tilde j. And now this cutoff is done in blue on these intervals, or slightly larger. So now there's a cutoff like this, there's a cutoff like that, there's a cutoff like that. But now these cutoffs, they are disjoint. They are not really talking to each other. Before it was a partition of unity, now they are disjoint cutoff functions. And so now you don't have to actually deal anymore with the fact that you need to understand what are the interactions of the two perturbations, because they're completely separate in time.
one problem, right? You're not able to inject energy. I'm thinking about describing energy. In that interval, you do not have opportunity to inject energy. You want each every step.
Yes, okay, yes. So yes, exactly. At each step, we want to inject energy. So how the hell do we actually solve that problem? You caught me. So, so we make it smart though. So we make a Galilean, I mean, instead of, instead of using horizontal stripes, we use diagonal stripes. Okay? I don't know if I'm making myself clear. So the stripes in Field's iteration is like this, but the stripes in our iteration, they are tilted. So our cutoff functions, instead of being pure time, they are a little bit time space. So our stripes are this way. So now we inject energy in the stripes, and every time slice is seeing an injection of energy. And because we are not, we cannot do the local energy inequality for sure because, it stays completely put in here. But I can do the global energy inequality because at each time slice, I'm actually averaging, I'm adding some energy here and some energy here, and what it really matters is the integral. So yeah, I was cheating before when I was just saying like, you just put this guy in here and it's going to do the same thing that it did in the, no. Because I'm not injecting energy, and you're perfectly right, in the stripes in which, I solved the Euler equation. But if I use this strip, and instead of using a cutoff or a partition of unity, which is pure time, but it's a little bit skewed, a little bit tilted, I shouldn't tilt it too much. There's some careful thing that you have to do, then I'm actually able to inject energy at every time. Because every time we see some portion of the space in which I see the stripe. It's an excellent point. Yeah, the part in which it is not white highlighted, I will not touch it. I'm solving Euler already, so I'm not going to. Yes, it is 0. Yes, exactly. It is 0. It is 0. So even the next, you see, you could ask, but then, the next error is also put in stripes. But my stripes become kind of smaller and smaller as I actually go along, right? So I need this kind of gluing step now. At the next step, these stripes are too big, right? Because I have a delta q to the 1/2 lambda q, it's going to be delta q plus 1 to the 1/2 lambda q plus 1 to the 1/2. So I will need actually much, much smaller stripes. So I still need to implement the gluing because I will need stripes which are much thinner. Yes, a little bit enlarged though, right? Because I need to cancel everything which is in there, and so my cutoff function will be slightly bigger. So it's not exactly only on the white, but on, maybe I go a little bit further away from the white region. The gap, so in this discussion, the size of the white stripes, the size of the blue stripes, and the gaps, they are all kind of comparable with numbers which are, I don't know, 1, 2, and 3, or I don't know, 1, 4, and 8, something like that. And they are all of the size 1/μ. You can play with these ideas though. So you can start, for instance, putting like, the stripes which are thinner, the gap which is larger, and like, I don't know, the cutoff. So there's lots of parameters you can play with, and you can do certain interesting things with them. That has to be said.
Okay, if no more questions, let's thank Camillo for this.